So this is a simple breakdown of NanoGPT Speedrun. If you are interested in learning how AI models are trained, but you want a basic breakdown of how the code is executed and what are the steps to execute that code, how to look at the logs, how to look at the profiler snapshots, and you're very confused as to where to start. So this is a very nice place for all those who are interested in AI and specifically in AI training, also in inferencing, because many of these skills are sort of parallel. And if you learn inferencing, there is some part of training that you'll understand because you'll understand the model itself. But this is primarily for AI training. So this is a basic breakdown of our speedrun baseline code. So we establish our baseline and then we try and move the needle. So our goal is to train the model faster. We are choosing a model similar to what the speedrun experiment chooses, a GPT small model, 124 million parameters. This is the, the entire lab is divided into 3 acts. So the first act is what we are looking at. Yeah, so the first act is what we are, where we are. Basically, in this act, we'll be running a code, and our aim is to run the model in the smallest possible time, reach our target validation loss of 3.28. So we will run through 6 iterations, and in each iteration, we'll see that the model trains a little faster. And for this, we'll use H100. So the first baseline run for us gave us a benchmark of 23 minutes on 8 H100s, around 6.44 billion tokens. And the next run, we expect the time to go down. So the way this particular experiment or the code base is divided, this is Act 1. So we are looking at what is essentially Tyler Romero's original code. So it's a very simple script, and these are the times that he had logged. So his baseline script was 8.13. For us, it is going to be 23 minutes. So we look at 23 minutes, and the next 6 iterations, we will improve our architecture, finish our speed run, then go to the next step. So the common beat remains the same. We complete our run, and then we look at the logs, we look at graphs, we look at profiler snapshots, and then we decide on the next thing, and then we keep on going till we are happy with our architecture. Right? So this is how a typical run would work. You would need 8 H100 GPUs. You would need a GPU provider like Model, Lambda, or any other GPU provider, E2E networks. Once you have 8 H100, the setup is ready. You can use the script to basically start your run. And once you basically fire the script, which we have done here, the provisioning setup will complete, and there'll be a compile and warm up step. And once the warm up step is done, you will see logs appearing on the command line, right? So this is the actual training that is going on. And after every 128 steps, you will see something like val_loss. And our aim is to take this loss from whatever value it is to 3.28. Once it reaches below that, or reaches that value or below that value, our experiment stops. We log the time and the steps. So as I said, for our run, it took us 23 minutes. And all the logs, the traces, and the profiler snapshots are saved in WANDB, and you can run that. You can download all those profiler traces and use any visualization tool. But what we have done is we have also done some amount of visualization here. So you can look at this canvas, and this is a profiler snapshot, and it tells you forward pass, backward pass. There was a step to sync gradients, and then you'll see an optimizer step in green. And you can even look at specific parts of the profiler through here, where you have got an all reduced bucket and then sync gradient and then optimizer. Similarly, you can look at other steps and details. So for every run, we'll try and upload these logs. The advantage being you can look at a screenshot from here, but you can also look at, we'll also show the detailed profiler snapshots as well. But that comes in to where we'll look at some key profiler traces. One of them being, so where is the act is on the top, I guess. Yeah. So this is the step where we look at profilers in detail. Maybe if you have gone to the point where you're looking at optimization on a particular GPU, writing custom kernels, that will be even more helpful, or you can even look at the overall steps. So this is about the basics of speedrun, and we'll be breaking down the code and everything. So the way to navigate this is you can basically join the event on the top event panel, or you can join from beginning, restart from basics. So let's go to restart from basics. So this is the basics part, basics. No, we'll go to the basic part. This is the basic part. So this is the basic welcome page, which we saw in the earlier video as well. And it talks about why 8 GPUs are required. It talks about DDP, and that's about it. And then there are, it talks about how to improve your fluency on this, on FBA Labs, where you can take part in events, complete challenges, complete videos, and you can gain fluency in this manner. So we'll go to the baseline. This is our baseline. And you can see on the left-hand side, you have the code. On the right-hand side, there is visualization. And we are looking at the model. And there is the data set, which is stored in model in this case. And then we start sending our batches to the GPUs, and we discuss. We go back. Yeah, to baseline. So we discuss the baseline setup in these blocks. So this is the code, and we have got various parts highlighted here in these blocks, which is the GPT model or the training loop, data loader in this case, not the training loop. And then the training loop is mentioned over here. You can look at this. Yeah. So this is the training loop, and then basics about DDP. So this is the DDP setup. So we are getting the rank and doing other things. So, which was discussed earlier, that how DDP works at a very normal level, right? So we'll look at our script. Before that, we'll go to I think this is the one. This is from an earlier cohort, very, very, very good cohort by Zach, Scratch to Sale. This is like the basis script there. We are not looking at this. We want our code. I'll just go from here to. Okay, so I'll navigate from my repo. It's called DDP training. We go to this bucket and we look at, there are two folders here. The first one is modern NanoGPT. This is the actual NanoGPT This is the actual speed run, right? So we are not looking at this. This we'll look at later. The first is, as we said, we want a basic breakdown. It is NanoGPT Speedrun, right? So we go into this and go into source, go into run files, and we have those 6 iterations that I spoke about. We are in baseline, and let me minimize this and increase the size a bit. Awesome. So this is our baseline code. And in this baseline code, we are looking at, so yeah, we have the code over here, and you can look at several classes on the right hand side. So the import section is pretty clear. I think we are also using NumPy. So we are using both PyTorch tensors and NumPy over here. And I think it is just for data loading. We'll discuss the difference between NumPy, Torch tensors, as well as D tensors, right? Which will be used which will be used later on, D tensors, for even more different kinds of parallelism. So right now we are doing 1D, which is basically DDP, data parallelism. So we have a target here in the file itself, hard-coded, and we have got attention blocks. So we go back to our FBA Lab and go to the model, right? So we are at 91, the same code, and we see the data class, and we have the config. So 12 layers, and we have the embedding size as 768 and block size as 1024. So we create the model over here, and stuck. So let me look at the code from GitHub itself. Pretty same. It's like the text is a little bigger, better for recording, So yeah, here we are. And what we'll do is we'll look at the sort of code, we look at visualization, and we look at this, right? So we have this architecture, and we have got, as I said, 12 layers. Yep. So we have 12 layers, and yeah, right. So we have some details at the bottom as well, and you can think about how many parameters are there and what is the architecture, which is given here as well. So then there is the distributed data loader part, and then there is a training loop, and then there is a setup, right? So this is the script, and let's look at the tutorial. So the way to navigate FBA Lab is we'll have lessons here. So this video lesson will be included in this section. You can read the text or the main text lesson or the blog here, but you have got additional topics, and we have got 2 things here. One is data packing, and the other one is optimizer that we'll look at, right? So let's look at the main section, which is, so we saw a sample run where we fired the command, and the training script ran on the GPU. And what happens in one run in a single picture is shown over here. So effectively, this is what you get. You have got the data which is kept in modal bin files for this code, but you can keep it wherever you want. Then we have got a loader script, and we are passing. So this is the structure. You have got the embeddings, you have the blocks, and then the head, and you are passing the data to the model, and you are calculating the loss, and then there is a backward pass, and where you are calculating the gradients. And after your communication is done, You then decide on the optimizer, in this case AdamW, and then on each of the GPUs, you update the model. So you basically get, after every run, you get an updated model on each of the GPUs, because you got basically we got the loss. We communicated the gradients to like all the GPUs. We got the gradients, and either by all reduce or reduce scatter. We have discussed both these approaches earlier. And once we have the gradients, we can average the gradients and then pass those back to all the GPUs, where we will get, where we can do the optimizer step. So you are basically at every GPU, you are locally updating. But if you look at it globally, every model then again is identical. Every GPU has the same identical model. So we started off with identical copies of GPT-2. We computed our gradients, we average them, we send those back to GPUs, and then we do optimizer at every step, right? So whatever, the loop was going to run as many times. In this case, it took us 24,000 steps or 23 minutes, right? So as I said, the bin files are where we keep the data. In this case, it is a tokenized copy of the model. So you have got data directly in int16, uint16 format. And right, so you don't need to run that heavy tokenization step. You can directly start with Speedrun. Then comes the data loader, right? And each rank starts reading at offset and strides. And the entire DDP data sharding scheme are basically these 4 lines in the script itself. So then comes the forward pass, then the loss, and then backward pass, and there's a clipping step associated with the optimizer. So we have discussed why the clip threshold is 1 and how it impacts the gradient. So to look at this, you will need to look at the graph of, so what we could do as ablation study is change the clip or not have a clipping mechanism and see how the gradients are impacted. So this particular WAN-DB graph, I think if I minimize this, we'll be able to see the full graph. So this is the training loss. This is the training loss, and so this is the gradient norm. And you are basically looking at validation loss. And if you look at the, and I need to zoom in. What I can do is I can reduce the size. And now the graph basically fit. That was my concern. The graph was not fitting inside. Right. So I'll zoom more. Yes, perfect. So we have got validation loss, which is what we are tracking. And we can see that it like starts up very high and then drops. And then you will expect the runs from 5K to, almost 24,000 steps. With this architecture, you see a very small sort of decrease in loss. And this is the training loss that you will see. So after every 128 steps, you will get the validation loss. So the sample training run will show you training loss. Every 128 steps, you'll see the validation loss. And then you can see the tokens seen. And of course, the step. So pretty like straightforward. We are tracking the validation loss. We're looking at the training loss, both losses. We are looking at steps. We're looking at step average as well. And in the next one, we are looking at the gradient norm and learning rate. So learning rate is like, we'll go up and then we'll reduce the learning rate gradually, right? and this is the gradient norm. So with clipping, you can see that the gradients aren't really exploding. So this is the graph that you can see by removing the clipping. So we were looking at the learning rate graph, and you can see that learning rate sort of climbs for around 250 steps, and then there is a decay part. Right? So there is a warm up part which lasts for 250 steps, and then our main training run. So from 250 steps all the way to 24,000 steps in this run is our main training, right? Okay. So let me check if this is getting recorded. I think so it is getting recorded. So we can look at the, sure. So we'll look at from this part. We'll go to our repo, and you can go to the NanoGPT Speedrun file, go to the source file, right? And go to run files as well. So the baseline script is here, but there is a run.sh file. If you click on this file, there are certain arguments that are there. So as I mentioned, that warm up iteration, the number of steps are 256, and we have a weight decay number over here, which is 0.1. Then we have total number of iterations, where after which this run will stop no matter what, right? Every 128 steps we will log the validation loss, and the gradient accumulation remains 1. So now let's look at the code where the actual learning rate takes place. So we'll go here. Go to the visualization part, training loop. The learning rate should also be here. There is a function called getLR, so we are more interested in that. So we are beginning training. Yeah, this is the function. So this is wrong. It says cosine with warm up. We are using a linear decay itself. So this is the code, and the code is pretty simple to understand. We have our warm up iterations as 256. If the current iteration number is less than that, we are going to basically return this as the learning rate. So you'll see the learning rate increasing, because essentially we are multiplying the learning rate, which is 0.1 divided by iteration plus 1, right? And just dividing it by the number of iterations. So if you are at like the first iteration, this will be 2 into 0.1, which is 0.2 divided by this number. This number remains the same. It's a constant. So this iteration keeps on increasing till we are at 256. Once we are at 256, we move to our main training part, where we talk about decay. So we have seen that the learning rate bumps up all the way to, what is the number? Not sure. This number 0.0015, I guess, and then goes down almost to 0.00243. Right. So we don't want the batches to have a over exaggerated impact on the gradients, right? We want a smooth learning, and we want to decrease the learning rate as we move forward. So we look at other code as well, from Olmo and from Marin code as well, also from small model from Hugging Face, and see how they have managed this as well. Also gradient norm, also clipping, right? So this is the training that is going on. Now we will go back to our code. So learning rate decreases. Why am I going here? You have to go back to our FBA. So learning rate decreases, and this is your decrease, right? So this is not a cosine. This is a very linear decrease. how does this work is, this is the learning rate which is being returned on every iteration. So if you plug in the iteration number here in the, yes, in the decay ratio, this is what reduces it. So you have got number of iteration minus warmup, which is again a constant, both of them, because your number of iterations are the max number of iterations that you are allowing, which is 25. So what you're doing is you are looking ahead. Once you have reached this point, you are looking ahead and trying to estimate how many steps are pending and how do you want to decrease the learning rate. Comes out to 9% decrease, but we will look at the code itself. So you are looking ahead and you are saying, okay, I have got these number of steps left. These number of steps have passed, warm-up iteration, right? Again, at the top, you have got this number where you are basically saying, this is my iteration minus my warm-up step. So if you are at 1256, so this number will come out to be 1000. So this number will keep increasing because we will go from 256, which is our first real run, to all the way to 24,000, right? Now this is our ratio. We will assert that the ratio is between 0 and 1 because that's what is expected, because you will never be able to go beyond the number of iterations that are available, which is, I guess, 24,000, because we have, let's check, because the number is here. Yeah. So this is 250. So it will be 24576 minus 256. That will be the maximum that you can go to, right? So your ratio is always going to be between 0 and 1, where you started basically your training, and then as this ratio, as you keep moving ahead with the iterations, your decay ratio number keeps on going up. So this is where the learning rate reduces, because you are returning, this number keeps increasing, so this numerator keeps on decreasing, and then you get that decrease. So I hope this is pretty clear, because you're just playing with the ratio and you are just playing with the iteration. So as the number of iteration keep on increasing, your decay ratio keeps on moving ahead, and eventually you are returning a lower learning rate on each iteration, right? So that's how it works. So this is the code for learning rate. Okay, so let's look at the baseline visualization. We have got data in .bin files. These are data shards, and we are interested in data loading. So what we need to do is we need to first set up our data loading script, where we worry about, first of all, some cleanup. We think about what if the data is correct or not. We just don't want to load data as is. So there will be two helper functions, and those two helper functions are, yeah, just use that. So we'll go back, we'll go to the baseline script, go to train the peak. So there is peak data shard, and there is load data shard, and then there is a main distributed data loader, which will be called for both training and validation loop, right? So going back to our FBA lab, so we want to first do some sanity check, which will be done by those two functions, and then we will load the data. We have got two things to consider. One is B and T. So we need to see the batch size, which is the micro batch size, which will be loaded per GPU, and the sequence length T, time or sequence length, whatever you want to call it. C is normally the embedding size or the dimension. So here we are talking about B and T. Now our gradient accumulation is 1 because we have got enough space. We have defined our global Yes, everything that is to be defined is here initially. So we have our global batch size, which is, as I said, B and T sequence length. So 32 into 1024 into 8 comes out to 262144. So keeping this same and keeping this micro batch same, we can pass on 32 into 1024 easily into each GPU, right? So per batch. What we can also do is, because H100 has a lot of memory, we can increase the micro batch and the total batch size. We are not doing it here because the model is small. But what would we do ideally is we'll look at our GPU and we'll try and fit as much data in one run, in one micro batch as we can. So when we are pushing the data, we can increase the batch size till we run out of GPU space. If you run out of GPU space, then the simple trick is you can use gradient accumulation. You can increase that number. So suppose that this was not fitting on your GPU, you would have gradient accumulation step as 4, and you would be able to work with that. So that's how the data loading basically takes place right now, where we are doing some sort of sanity check. Then we are focused on creating the batch, preparing the batch so that we can pass it on to the training run, to the forward run in this. And the same thing for a validation run as well. Right, so can see that visualization here. So we're just trying to understand the base script, and there'll be improvements in data loader because that's one of the steps there. So there is a detailed discussion on DDP setup. So we'll stop here and we'll just look at what is there in Rune. Again, there are optimizer basics, and so we are using Adam. So what mostly Muon is going to be used in the next iteration. So we basically start from what is an optimizer and stochastic gradient descent SGD. Then we build Adam, and then we look at AdamW. That's the step. You can even look at the original papers in the next few videos. And so right now, and then there is data packing as well, which is the core nature of why we look at data packing also. This is the data packing is already part of this iteration itself. And packing versus padding. So how padding what are the issues with padding and how packing is done, and how packing is managed by other packages as well. For example, Unslot. And we'll look at code from other LLMs as well, which includes runs like small model from Hugging Face. We can look at Marin. We can look at Olmo, which is pretty cool. They have the entire training script. So we can look at padding, how is it done there, even if the code is available in terms of DeepSeek, but I don't think there'll be much information about how packing takes place from the tech blogs. Maybe it's there. We look at DeepSeek and other, maybe Quen blog. There is a very good blog by MinMax as well. So we can look at any of those blogs and see how things are done. There is a lot of details on how Unslot does packing here and how packing works. So, but I'll just keep the video very basic because we are just looking at the breakdown of the script, and we will go into details of all of this later. So this is the main tutorial, and the text lesson is there, plus the main section is there. I don't think I've missed anything. This just talks about the bin file. This talks about the clipping and the gradient, and this just talks about how the training takes place. What is it talking about? 10, 10, 10 loss. Okay, so this talks about the loss, how the updates take place, basically. And this is a screenshot of the terminal. And you can see that you will see training loss, but after every 128 steps, you will be able to see uh, the validation loss, which you saw in the earlier simulation as well, right? So training loss versus, you can see the jagged part is the training loss. And why is the training loss so jagged? And why is the validation loss sort of smoother? That's a question that you can ask. And when does it stop? It stops either when we reach 3.28 or when we reach this step. This step is defined in the as an argument in the script itself. So we look at some WANDB logs, WANDB graphs, which we have already seen. We've seen learning rate, we have seen the step average, which is the time, and we have seen training loss as well as validation loss. So this is just so you can see there are random spikes here and before clipping at once. So spikes above the line never reach the weight. And we have that clipping. So we don't have massive jumps in gradient. Right. And we have discussed about gradient accumulation as one. So when Tyler worked with his initial script, he had smaller GPUs, and so his gradient accumulation number was 4. Right. So and we have kept the same global batch size, so we have to keep the gradient accumulation as 1 because everything just fits very well into our GPUs. We can increase the global batch size as well as the micro batch size to a large extent. You can load a bigger model as well because H100 has got a great amount of memory in it and can hold larger weights and can push the data there. You can actually pass a bigger batch size. Bigger batch size, bigger. You need to keep space for everything: batch size, the weight of the model, and the gradients as well, and the optimizer as well. So like all of this combined is your memory that is there, right? So this is about the breakdown, and the main lesson. We'll look at some advanced deep dives in Rune. Rune is our AI assistant. So we are keeping some topics over here and we'll integrate more AI. So right now these breakdowns are manual. So we have given a lot of context. What Rune will do is it will help you ask questions specific to these topics and go deep dive into it. So we call it Rune topics, even if it's manual breakdowns. These are all manual breakdown. And if there are videos, you'll be able to see additional videos on top as well, right? So that's it. See you in the next part. Bye.